Friends, in this video, we would learn about potential difference and how potential difference can be defined in terms of work done per unit charge. Also, we would learn about the relationship between electric field and electric potential, and we would establish the fact that electric field is negative gradient of electric potential. Later by the end of this video, we would learn about what are equipotential surfaces and the properties associated with equipotential surfaces. So friends, let's begin with what do we mean by potential difference. In physics, the term difference itself stands for subtraction of a bigger value minus the smaller value. So whenever I am using the word difference in physics, I always mean to suggest to you that you have to subtract a smaller value from a bigger value. So if I am talking about a potential difference, so potential difference eventually would mean a higher potential minus the lower potential. And since you are always subtracting a smaller value from a bigger value, so difference will always be a positive quantity. So suppose friends, in space I have got some uniform electric field which is directed from top to bottom as you can see, and there are 2 points, point A and point B. Now recall from our earlier discussion about electric potential and properties of electric potential. Over there I told you that electric potential decreases in the direction of electric field. So you can see the point A and point B. So when I move from point A to point B, the potential would eventually decrease because I am moving in the direction of electric field. So friends, point A will be at a higher potential whereas point B will be at a lower potential. And also in that particular video, I told you that whenever a free positive charge is kept in such electric field, the free positive charge would always tend to move from the region of higher potential to a region of lower potential. So if I am going to place a free positive charge over here, so the free positive charge would always move from the region of higher potential to a region of lower potential. So point A is always at a higher potential whereas point B would always be a lower potential. Hence I can define the potential difference as VA being at a higher potential minus VB. Now friends, since the charge moves on its own from the region of A to B, you don't have to do any work. Rather, you will be obtaining the work. So work will be done whenever I am going to move the charge from the region B to the region A. Hence, work done per unit charge. Over there, if you remember, I told you work done per unit charge. So in this case, and work done by whom? Work done per unit charge by the external agent. So the work done per unit charge by the external agent in order to move the charge from the region B to the region A will define the potential difference between point A and point B. Is that clear, friends? Let us move on to the next slide and that will become much more clear to all of you. So friends, as I told you that a free positive charge would always move from a region of higher potential, that is from point A to point B. So work would not be done, rather work would be obtained. So in order to do the work, what is required? It is required that I must place the charge at point B. Now if I place some charge at point B, then in order to move the charge from point B, that is the region of lower potential, to point A, the external agent would need to do some work. So what is needed? I place the charge at point B and then the external agent has to do some amount of work in order to move the charge from the region of lower potential to a region of higher potential. Now this work done per unit charge by the external agent would define the potential difference between point A and point B. So the potential difference between point A and B, so VA being at a higher minus VB being at a lower, so potential difference VA minus VB would be equal to work done per unit charge by the external agent in moving the charge from the lower potential to the region of higher potential, because from a region of higher potential to region of lower potential the charge moves on itself. You don't have to do work, the work will be obtained, but as per the definition of potential, work done by the external agent used to define the potential. That is the reason why I am saying that the potential difference between any 2 points in electric field can be defined as work done per unit charge against some sort of conservative force. Here in this case it is electric force. So work done per unit charge in moving the charge from lower potential to a region of higher potential, friends. So work done is equals to Q naught times potential difference. How? See, this is the work done. Take Q naught over there. So work done into, so work done is equals to, I am taking this Q naught over there. So work done will be equals to Q naught times potential difference, and that's what the relation you have got. Work done will always be equal to Q naught times the potential difference between those 2 points, friends. Now, also remember, work done in mechanics was defined as change in kinetic energy, isn't it? So work done was defined as change in kinetic energy. So I am just putting this value as change in kinetic energy over here. So change in kinetic energy is equals to Q naught times PD. So in electrostatics, friends, whenever you been asked for kinetic energy of a charged particle, please remember kinetic energy of a charged particle as Q naught into PD. Do not jump as kinetic energy as half mv square. In electrostatics, whenever somebody asks you kinetic energy, start thinking in terms of Q naught into PD. Work done also has Q naught into PD. Take care about this important fact. It will help you in lot of numerical problems, friends. And this is going to be one of the most important topic of electrostatics that you need to complete up. Now, this also defines 1 electron volt. So friend, how do we define 1 electron volt? 1 electron volt is defined as the kinetic energy acquired by an electron when it is moved through a potential difference of 1 volt. So 1 electron volt happens to be the kinetic energy acquired by an electron. Kinetic energy acquired by an electron when it is moved through a potential difference of 1 volt, isn't it? So 1 electron volt is equals to kinetic energy, and what is the formula of kinetic energy? That is Q naught into PD. And what is the charge of an electron? That is 1.6 into 10 to the power of minus 19. And what potential difference across what potential difference you are moving? You are moving the electron through a potential difference of 1 volt. So 1 electron volt eventually will be equal to kinetic energy, and which is 1.6 into 10 to the power of minus 19 joule. Now friends, this becomes an important conversion factor in electrostatics and atomic physics. 1 electron volt is equals to 1.6 into 10 to the power of minus 19 joules. Okay friends, let's now try to derive the relationship between electric field and potential difference. Suppose there is some charge which is placed in uniform electric field, and let's say that charge is Q naught. And as I told you, the work will be done in order to move this positive charge from region of lower potential, that is the point from point B, to a region of higher potential, that is some point A. So the agent needs to apply some force in overcoming the electrical force, the conservative force, and then by moving the charge from B to A, it will be doing some amount of work done. Now, as I just now told you, work done is equals to Q naught times PD, and if the charge magnitude was Q naught, then the work done by the agent would eventually be Q naught times PD. And in doing this, the agent has moved the charge through a displacement of delta x. So what the agent has done, he has moved this charge to a displacement of delta x, that is from B to A. The displacement suffered by the charged particle is delta x. So work done from mechanics will be equals to whatsoever the force that the agent applies. What is the force that the agent applies? I'm calling it as FAG, and the displacement suffered by the charge happens to be delta x. So the work done by the agent from mechanics, work done by the agent from mechanics. So from mechanics, work done by the agent will be always be equal to force applied by the agent into the displacement suffered by the body in the direction of force applied. So the force applied is in the upward direction and the displacement suffered is also in the upward direction. So force applied by the agent into delta x will give me the work done, and this work done from the mechanics and the work done from the electrostatics must be the same. So what I have done, I have equated both the work done by the agent is force applied by the agent into delta x is equals to Q naught into PD. Now remember friends, the force that the agent is applying, he is applying the force against the conservative force, against the force of the electric field, which is F is equals to Q times E. So the force applied by the agent is acting against the direction of the conservative force, against the direction of the electric field force. So this is the force which is being applied by the electric field, and this will be equals to force applied by the electric field on any charged particle was equals to Q times E. So this will be equals to minus Q times E. So the force applied by the agent will be minus times of Q times E. So what I am going to do friends, I am going to substitute this force over here. So this becomes force applied by the electric field is Fe into delta x into Q naught into PD. Now force applied by the electric field was QE, substituting it over here, so it becomes minus Q naught E into delta x into Q naught into PD. Now what is PD? PD happens to be the potential difference between the point A and B. So let's assume that the potential difference of point A. So let us assume that the potential of point A, potential of point AB, V plus delta V, because A is at a higher potential. So as I move in the direction of electric field, the point B will be at a lower potential, and let's say the point B potential to be V itself. So what is the potential difference friend then? So potential difference is higher potential minus the smaller potential, that is VA minus VB, that is V plus delta V minus V, and that happens to be delta V friends. So what I have done, I have substituted this delta V over here in place of potential difference. Now friends, Q naught and Q naught are same, they cancel out from both sides, so I get a relationship between electric field and potential difference as E is equals to minus delta V by delta x, that is electric field is negative gradient of potential difference. In calculus notation I would write it down as E is equals to minus dV over dx. So this is the calculus notation of the expression. So electric field is negative gradient of electric potential. Now let us understand what are equipotential surfaces. As the name itself suggests, equipotential surfaces means it is a surface which is being obtained by joining all such points which are at the same potential. So I can define an equipotential surface as the locus of all the points that are all at the same electric potential. For example, let's take a point charge Q located in the space, and if I take the points which are situated at the same distance from the charge. So you can see this point, this point, this point, all these points are located at the same distance from the charge, and the electric potential due to a point charge is inversely proportional to R. So if this distance R and this distance R and this distance R is going to remain the same, so this point, this point, this point, all these points will be at the same potential. So what I am saying, as you all are aware of the fact that potential due to a point charge is given by the formula 1 upon 4 pi epsilon naught Q by R. What is Q? The magnitude of the source charge. What is R? R happens to be the distance from the source charge. My source charge happens to be this. So this point P1, let's say it is situated at some distance x. This point P2 also situated at the same distance x. So the potential of P1 and P2 would be the same because they are located at the same distance from this point charge Q. Let's say this is point P3, which is located at the same distance x. This is point P4, which is also located at the same distance x. So all these points P1, P2, P3, P4, they are the points of same potential. So when I join these points and I obtain a surface, then this surface is going to be referred by us as an equipotential surface. So this surface is going to be referred by us as an equipotential surface. So in three-dimensional space or in three-dimensional space, a sphere around a point charge is going to define the equipotential surface. For a two-dimensional space, it will be a circle around the or concentric circles around a point charge will define the equipotential surface. So all points on a sphere around a point charge will be the surface which is going to define the equipotential surface for a point charge. Now if suppose there are two parallel plates, then you all know, neglecting the end effects or the fringing effect, the electric field will be directed from a positive charge to the negative charge. Now as I just now told you that along the direction of electric field, so if I move from this point x to this point y, so along this direction the electric potential always decreases. But if I take up the points on the plane parallel to the plates, can you see all these points which are lying on a plane parallel to this particular plates? So P1, P2, P3 and all these points which are lying parallel to the line in the same plane and parallel to the plates, they are going to have the same potential. So this line that I have drawn, this dotted line that I have drawn, would be the line which is going to show the equipotential surface. So for points or between the two plates or through a uniform electric field, the points which happens to lie on the same plane parallel to the plates define the equipotential surface, friends. So this was some of the two common equipotential surfaces that you might be asked in your board examination. Another very important aspect of equipotential surfaces are the properties associated with the equipotential surfaces. Let's go through with those properties also. The very first property says no work is done either by the Coulombian force or by some external agent in moving the charge along any equipotential surface. Now why there won't be any work done? As I just now told you, work done is equals to Q naught times PD. Now if you are moving along the equipotential surface, being an equipotential surface, potential difference will be zero. Both the points would be at the same potential, and then only they can become a equipotential surface. So in that situation, work done, potential difference is zero. If potential difference is zero, then eventually the work done will also be zero. Is that clear? So no work is done either by the Coulombian force or by some agent when we are moving a charge along the equipotential surface. The second important property says that electric field is always perpendicular to equipotential surface. Now, why electric field is perpendicular to any equipotential surface? Let's try to understand that. Now, work done is always equals to force into displacement in the direction of force. So, force F dx cos theta. From mechanics, you have studied this. Now, in case of electric field, the force that is going to be applied by the electric field or by the agent must be QE into dx into cos theta. Now, if it is an equipotential surface, so work done along the equipotential surface is always zero, as just now in the first property I have told you. So work done will be zero. if work done is 0, now Q is non-zero, E is non-zero, displacement is non-zero, then when can the work done be 0? When E will be perpendicular to displacement, isn't it? So electric field will always be perpendicular to equipotential surfaces, friends, because force will always be directed in the direction of electric field. Remember my earlier discussion, behavior of charged particle in electric field. So that is the reason why electric fields are perpendicular to equipotential surfaces. And the last property says no two equipotential surfaces intersect each other, because if two equipotential surfaces intersect, suppose this is one equipotential surface and having a potential of say 5 volt, this is another equipotential surface which is having a potential of 4 volt, then at the point of intersection I will have two different potential, which is itself not possible. That is the reason why no two equipotential surfaces can intersect. This is one equipotential surface of 5 volt, 5 volt, 5 volt. This is another equipotential surface of 4 volt, 4. But at the point of intersection, I will get two different potential. Na? One due to 5 volt and another due to 4 volt, which itself is not possible. At the same point, you cannot have two different potential. That is the reason why no two equipotential surfaces intersect each other. So friends, this was all in this particular video. Go through this. If you haven't watched earlier videos on electric potential and potential energy, you can click on the top right hand corner I button, and you would get the playlist of all the video lectures that we have discussed in electric potential and potential energy. Go through it. This chapter is of importance for you all for the ISC examination, so please take care, and especially for 2020 friends. 2021. Friends, thank you for watching. Don't forget to give a like or comment. अगर अभी तक आपने मेरे इस चैनल को सब्सक्राइब नहीं किया है तो please do the same. Don't forget to hit the bell icon so that whenever a new video is loaded, you get the notification. Take care, and we will meet back again with a new video and a new solution. Thank you, friends.